slow it down even more. So over here, it's kind of a little hard to see. It's going up again, but one thing, there's two phenomena. I'm going to draw them both on the board for you. It's a lot going on. This demo's got a lot going on. All of it you want to know. So what did I just show you? I showed you that if I have a tube, so I got a tube right here, water's flowing in, it flows along like this. Okay, I got some tube. And there's standpipes that are coming up like this. There's a couple over here too. In fact, the way the device is built, there's actually 6 standpipes, and there's something else I didn't draw accurately in this drawing about it. And that is, these middle standpipes are in a region of the pipe that's narrow. There's a restriction in the pipe. Constriction. All right? So that's the way it looks in reality. So that's what I've got. 6 standpipes, 2 in each section. There's a middle section that's narrow, and the side sections are big, really thick. And so that means that when you go from this part to this part, you can use Bernoulli's equation to relate, like here's point 1, right? You got pressure 1, you got velocity 1, the water's going that way, velocity 1. You got area 1, this big area right here, right? And then you can compare over here, area 2, which is much smaller, you got pressure 2, and you've got velocity 2. So velocity 2 must be bigger by the continuity equation. You might say, wait a minute, what do these standpipes do? Well, the water's not going up in the standpipes, it's flowing along like that. So we can just think of the standpipes as not part of this continuous flow. We can use the continuity equation to relate the velocity and area here to the velocity and area here. And the area here is smaller, so the velocity must be bigger, right? V2A2 equals V1 A1. Big A, little v, little a, big V, right? Fast moving in here. Now what about the pressure? If we use Bernoulli's equation to relate this point to this point, and we can ignore the rho gh part because the heights are the same for these 2 points inside the pipe. Heights are the same. What does it say? Bernoulli's equation says between 1 and 2, right? It says that pressure 1 plus 1/2 rho v1 squared equals pressure 2 plus 1/2 rho v2 squared. And remember, I got rid of the rho gh because they're the same in both places, so it cancels out both sides of the equation. And lo and behold, sure enough, if you're moving faster, as you are here by continuity equation, bigger v2, you better have a smaller p2 that corresponds to the same values over here. So it's counterintuitive. I've proven it to you in what may be an unsatisfying way, because it doesn't give as much intuition as it might. Ooh, I don't know if I can move this thing out of the way without hurting myself. Oh my goodness. Yeah, I just want to get out of the way so you can see the board. But another way to think about it is like this. What makes the water move fast right here? It's going lickety-split, it's going slow over here. It's going fast because the pressure is big over here, and the pressure is small over here. So that means that when the water went from here to here, it was accelerated forward. Bigger pressure behind, smaller pressure in front, sped up. That's why it's fast here, slow here. That's another way to intuitively see why it must be true. You know it's counterintuitive. The pressure is lower here than here. And I measured the pressure with the standpipes. Standpipes said, oh yeah, I got high values there, low values here. Why are they low? Because the pressure is lower down here. How do you calculate it? You say there's a little membrane here at the bottom of the standpipe. I'm going to pretend that no water, it's true, no water goes up this way. So you're not allowed to use Bernoulli's equation to go from this point to this point, from below to above the bottom of the standpipe. But what you can do is the same thing we do at the surface of the water. When we say there's 1 atmosphere above the water and there's 1 atmosphere just underneath the water. Same thing here. P2 right here is the same thing as P3 here. P3 and then P2. So I'm going to cut to the chase a little bit. I'm going fast, I know. I'm sort of giving you a heads up of all the techniques and ways to think about these problems. You're going to use these sort of tools to solve fluid problems. I'm going to say a little bit about the midterm, so I don't want to spend too much time. But anyway, P3 up here, same as P2. For the same reason that the pressure below and above the surface of the water is the same. You do Newton's second law on a little piece of water right there, and that's what you get. But the velocity here is 0. The velocity here is V2. So V3 is 0. So Bernoulli's equation would give you the wrong answer as you went from here to here, because the velocities are different, but the pressures are the same and the height's the same. See what I mean? So don't use Bernoulli's equation to go from here to here. It's not one continuous flow of water. Bernoulli's equation works from here to here. Bernoulli's equation also works from the bottom of the standpipe to the top of the standpipe. How tall is that? Oh, it's the pressure down here equals rho gh. That's how you calculate the height. Why is the height lower here than there? Because the pressure is lower there than it is there. Standpipes measure pressure by showing you the height. Why was it low over here? Same area here is there. It should have been back up. It's because of viscosity. Viscosity is yet one more thing on top of all this stuff. Viscosity is like friction. It's a dissipative force. It's a way to remove energy from a system. The continuity equation is always true, even if there's viscosity. Half of you will never believe me, but it's true. Continuity equation, this equation for water, for an incompressible fluid like water, is always true, even if there's viscosity. What does that mean? It means that if you lose energy due to viscosity as you move through the pipe, it can't come away from the kinetic energy. The kinetic energy has to be what it is because of the continuity equation, because of the geometry of the pipe. Just can't get around that. So where does the energy come away from? What energy term? The height's the same, the velocity's the same. What can you do to remove energy from the system? What's the third thing in Bernoulli's equation? Kinetic energy, gravitational potential energy. Pressure. Pressure goes down. That's why these things are going down. Viscosity, lowering the pressure in the water. If you can fathom that, you're doing great. Right? I told you a lot of stuff right there. You're going to learn this for real when you solve problems in a week and a half on homework and get office hours and stuff. But I want you to at least see it before we move on. It's too much stuff to cover in class, it's true. But it's fun stuff. There's a lot. Okay, so good. That's my whirlwind tour. Let's really quick prove to you that that pressure is for real. I'm going to make a can out of this. Here I've got a ping pong ball right here. I got a 2-meter piece of tube. I'm going to go ahead and evacuate the tube so that there's 1 atmosphere pressure on this side of the ball, 0 pressure on that side of the ball. How much work is that? What's work? Force times distance if it's constant force. It's loud. This is loud. I'm going to give it 20 seconds. I'm going to burst what's smoking? I'm going to burst a membrane over here. Piece of tape. And these are Coke cans. So if this is Coca-Cola, they're empty. It's Coke cans. And I'm just going to break the tape. And then 1 atmosphere of pressure in the room will hit this side of the ball. 0 pressure. And we'll see how fast it winds up going. I'll say 1, 2, 3, and come on. I'll do it. All right. 1. You can close your ears. 1, 2, 3. It worked. Yeah, it worked. It wasn't as loud as the, oh, it didn't make it through, only made it through 1 can. Usually I destroy 3 cans, but yeah, there you have. But anyway, so, but it worked pretty well. Yeah, so we can go through the calculation. I want to talk a bit about the exam. So if you do the calculation, it turns out it's going 600 miles an hour. Let's take my word for it. But the point of that is that the pressure in the room is a real deal. There's really a lot of pressure in the room, 15 pounds per square inch. You don't feel it because the pressure inside is the same. If you remove the pressure on the other side, and we could calculate it. You should be able to calculate that. You know, how much work was done, how much damage and energy was done. Just calculate the work. It's force times distance. What's the force? There's an area on the side of that ball. Just think it's a cylinder. Think of the area. Multiply that by the, what is it? It's pressure. Pressure is force over area, right? So to get the force out, you multiply. Anyway, you figure it out. Great. So now how about the exam? So you know what's going to be on there. But I'll tell you again. And one thing is, You can use a cheat sheet, or it's not a cheat sheet, you're not cheating. Use a formula sheet. 2 sides, both sides. You can use the one you used last time that was one side, and right the other side, that's fine. But you can bring a brand new one. Suppose last time you thought, oh, this was a lousy formula sheet, I didn't have all these things I wanted, I had a lot of stuff that I didn't need. You can change it. But you're allowed to use the same one again. That's why I make it one side the first time, 2 sides the second time. Don't overdo it. Don't do that with that student of mine with the 3 different colors and different colored glasses and like writing outside. Don't do that. Make your life simple. No microfiche, right? Make it really, you don't know what microfiche is. No small writing. Make it legible, make it easy to find the stuff you want, right? That you need, right? No, and so what's going to be on the exam? It's chapters 9, 10, and 11. Okay, no surprise. Oh, excuse me, 9, 10, and 12. Chapter 11 is not going to be on the exam. 9, 10, 12. I know I'm laughing and you're crying when I say chapter 11. Chapter 11 was angular momentum, I think. No angular momentum on the exam. No angular momentum. But there will be angular acceleration. There will be angular velocity. There will be moments of inertia. You will not have to calculate using some big nasty. You can't. You're allowed to. You will not be required to calculate moments of inertia that involve integrals and stuff like that. But you might have to figure out what it is based on some other information. Like maybe I'll give you the moment of inertia about one point in the object, and you'll have to figure, or one through one axis, right? And you'll have to then figure out what it is at another point. What would you do if you have a situation like that? The parallel axis theorem. Parallel axis theorem, right, tells you how to relate the moments of inertia between the center of mass and some other pivot point. Oops, sorry. Is it plus or minus over here? Plus. Moment of inertia center of mass is the smallest moment of inertia you can have about any axis parallel to the one in question. And you get an m times d squared, I guess, where d is the distance from the pivot point to the center of mass, right? Very important. What about kinetic energy? There's rotational kinetic energy that's going to be on the exam potentially. And actually, you'll have your choice in some cases. You can solve some problems using Newton's second law for rotations. Other problems, or that same problem, you could also choose to do it using conservation of energy, where rotational kinetic energy is one component, right? It's one part of that. So what is that? How does that work? Kinetic energy total, what does that equal? It's the kinetic energy of the center of mass. And I don't mean about the center of mass. I mean the linear. This is linear kinetic energy of the center of mass. It's 1/2 mv squared, where m is the total mass, right? And v is the velocity of the center of mass. Everyone agree with this? It's that plus kinetic energy about, let's see, I'll write alpha to mean rotational kinetic energy, and it has to be, about the center of mass, right? So this is totally valid, but sometimes you might, it turns out there's another way to write this. This turns out to be the same thing as the kinetic energy of rotation about a stationary point. A stationary point. So I meant to write about, so around a stationary point. Now, in some problems, there is no stationary point. If I have a wheel, there's a bunch of 4 old midterms on the website you can check out, right? I hope you are checking them out. There's one with a wheel that's rolling off a roof, and it comes off the roof. It's falling through the air. Well, there's no guarantee that any point of that wheel is stationary, right? So on that problem, you probably say, okay, if I use kinetic energy, I'll add the kinetic energy of rotation about the center of mass, and add that to the kinetic energy of the center of mass, the linear kinetic energy of the center of mass. What is the formula for KE rotation? Something I hand up, actually. What do you have a question? Sorry, where? This one? Oh. It has to be. I said it right and I wrote it wrong. I think you're right, because the smallest moment of inertia has to be center of mass. Yeah, you guys are keeping honest. So I said it right and I wrote it wrong. I looked at it, it seemed right to me. But yeah, if that's the smallest it can be and that's a positive number, then it better be this way. That is correct. Let me make sure that's right. You think about that. If I have, suppose I have some object, and this is the center of mass of the object. So what is the formula? You may have to calculate moment of inertia like with discrete pieces, right? What is that? Moment of inertia, the definition is that you sum over all the parts, and you say m of the mass of each part times the radius squared of each part. And it's the perpendicular distance, the distance from the pivot, or the axis of rotation to the piece of mass in question, right? So, right, I think you're right, because this thing, to make this as small as possible, like this feels like r squared, right? I want to make r as small as I can. The way to do that is to take the distance r, to measure it from a pivot point that is as close to the middle of all the mass as possible. So you're absolutely right. This is the smallest thing. I think I said it right. I just wrote it wrong in the equation, which would not do me any favors if it was a test. So this thing right here is the smallest moment of inertia you can have. And the moment of inertia can be bigger by choosing it to be off away from the center of mass. That's right. And this is the formula. You may have to use that. You may have to calculate moment of inertia by saying, oh, there's a teeter-totter, and there's a child on one side and a large person on the other, and they have different masses and different weights. And you'd say, okay, what's the torque or whatever, right? And you calculate the moment of inertia. Now when you do that, you have to know, am I including the people on the teeter-totter as part of the moment of inertia or not? If they're holding on tight, the problem description says if it's an object that's nailed onto it, if they're holding on tight, they're part of the moment of inertia. They're rotating with the teeter-totter. But if they're just flopping around, or if there's no friction, you got something resting on it, right? In that case, they're not part of the moment of inertia. It's a little bit tricky. I'm mixing subtleties right now more than I should. The big picture is, yes, thanks for getting that formula right. Appreciate that. What is the kinetic energy for rotations about some pivot point? Well, it's just 1/2 instead of mv squared, it's I omega squared, right? And when I measure I, it better be about the same pivot point. If I want this thing about the center of mass, better use the center of mass moment of inertia, right? Got to match up. One thing I want to emphasize too. So what else is not being covered? We're not going to cover any 2-dimensional collisions like billiard balls and stuff like that. But there's probably going to be collisions on the exam, so know how to recognize when you see a collision. There's an old test problem, right, where Stupendo is shot from a cannon and he grabs a ball. Is that a collision? Yeah. It's inelastic. Is it maximally inelastic if he grabs the ball and holds on to it? Yes. When two things stick together, or vice versa, how about shooting a bullet? So the bullet's in the gun, holding still, pull the trigger, and now the bullet flies out of the gun. Is that a maximally inelastic collision? Bullet being fired from a gun? Well, were they stuck together at the beginning? Yeah, they weren't in the end, so it's sort of time reversed, it's backwards, it's not collision in that sense. But in terms of the equations we use, yes, the math is exactly the same as, and I would refer to it as, a maximally inelastic collision, shooting a bullet. Because you start off, everybody's holding still, and then they blow apart, and they're not stuck together anymore. So, yeah. What is kinetic energy preserved in a maximally inelastic collision? So if I'm flying through the air and I grab a ball that's held up on a pedestal like the guy in the problem, is the kinetic energy conserved? Is my initial kinetic energy equal to the total kinetic energy of me plus the ball flying at the end? Yeah? I don't believe it. Did it go up or down? Down. Kinetic energy is lost when I'm flying through the air, or when something's moving and it collides with something else and they stick together. Kinetic energy is lost. When I say maximally inelastic, inelastic means kinetic energy is lost. Maximally inelastic means that as much kinetic energy was lost as could have been lost. Maximally, right? In fact, if you view it from the center of mass coordinate system, the kinetic energy goes to 0 at the end. Because the two objects, so if I'm flying, suppose something's flying along this way and there's a ball holding still right here. I'm at the center of mass, so I'm walking along, watching these two objects, right? Then they collide, and they're together. they're still holding, in my reference frame, they're not, oops, in my reference frame, let's spell there. My reference frame, they're stuck together and they're not moving. Kinetic energy equals 0. But they initially had non-zero kinetic energy. Initially, this guy was moving toward me and he was moving that way. From your perspective, this thing wasn't moving and that was moving. In both reference frames, the kinetic energy was non-zero before and smaller later. In the center of mass coordinate system, it was non-zero now and then 0 now. It's not moving in my coordinate system. For you guys, it's still moving. There's still kinetic energy, but it's less than what you started with. And the amount of kinetic energy that was lost is the same in your reference frame as it is in mine. So collisions are probably going to show up on the exam. You want to recognize one when you see it, right? There's a problem for an old exam. Actually, there's some old exams that have fluids problems. Don't sweat it. No fluids on this exam. But I saw the old exams were at different parts of the semester, and so fluids recovered before the exam came out. That's all. But there's an example of a collision problem where there's water shooting out of this thing and lands in a cart, and it's a collision problem. You solve it by using. So what do you use? If you want to figure out what the final velocity is for Stupendo holding onto the ball after he grabs it from flying through the air, you know its initial velocity, say. You want to know what the final velocity is. You use conservation of kinetic energy. Is that going to work? No. What are you going to conserve? Momentum. Conservation of momentum will solve that for you. Conservation of momentum gets you in trouble sometimes if you have a gun that's anchored to the ground, because in that case the Earth will soak up the momentum, right? Like we did, we shot a bullet and we measured the muzzle velocity of the gun. That's a situation where you have to use something else to use the chemical energy is in the gunpowder or something, and the efficiency of the gun. Geez. But in terms of collisions between things that are not anchored to anything else, yeah, conservation of momentum always works in that case. Let's see. So, right, I mentioned that. Right, and we're only no cross products or right-hand rules. If you want to use them, right on. We're not going to need it for the exam. Torque is going to be treated like a scalar quantity. It can be positive or negative. Better give me every problem you've got. You got some status problem. There's a homework problem, right? With this dresser. Does everyone like this problem? Kind of fun. Reminds me of home decoration and stuff. You have a normal 2 and a forced. What is it? Normal force, no, frictional force. I'm using different notation than they use. If you have a problem like this, you may want to have separate normal forces defined in different parts of the object, right? You're pushing over here, F push, right? Gravity acts at the center of mass effectively. You've got upward force due to normal over here. I'm using N like the book's notation, but you might use F sub N. Doesn't matter. Problems are clear. Look at all the forces in this problem. I just want to check real quick. When you're calculating torques, let's get our signs. Just right now, let's make sure we understand signs right, and let's make sure we understand how to read it off without doing any calculation. I don't want to use Pythagorean theorem if I can get away with it. I don't want to attach without a calculator. I don't like doing that. I don't want to have to do. I want to do things the easiest way I can. So if you know that that's H, and you know that that's capital H, and you know that this is L, right? Let's calculate the torque. Let's choose this as our pivot point. For no good reason, I'm just doing that for fun. I'm allowed to because this is a statics problem. You may say, wait a minute, what is the problem? Somebody's pushing their desk along the ground. Let's say that the desk isn't moving right now, or their dresser. Even if it were moving at a constant rate, we can still treat it as a statics problem. That's okay. It's not accelerating. But let's make our life easy. It's not even moving. It's just holding still on the ground. I'm pushing on it right here. I want to calculate the statics problem. I want to calculate the torque. Maybe the question I'm asked is, what's the normal force over here on this leg on these legs of the dresser? The combined normal force of these legs over here. How do I do it? If I choose this pivot point, if I get a non-zero torque from N1, one person's like this. Appreciate that. Yes, you bet. Because that's the radial arm, right? What is the radial arm? L, H, capital H, sine of beta, what is it? If that's my pivot point, and that's where the force is acting, it's capital L. And if this is my positive direction, look at the homework problem, that's going to be the other direction for positive. Suppose I chose clockwise, my positive direction for torques. If that's my pivot point, do I get a positive or negative contribution of torque from N1? Positive. Put a nail in right there, which way does it rotate? How about from gravity, positive or negative? What is its value? What is the value of the torque from this right here? About this pivot point. Just read it off. No need for angles. What is the perpendicular component? So here's the direction of the force. Perpendicular to the force is that way. So if I take this radial vector from here to there, it's got a horizontal component and vertical component. How long is the horizontal component? L over 2. The torque is negative mg L over 2 times, that's it, negative mg over, I'm off to the next part of the problem. No sine beta needed. I just read it off. If you know how to do that, you can save time on the exam. Anyway, the one thing I want to emphasize too, now, maybe one more minute, I'll say one more thing. And that is that a lot of students are confused about the difference between Newton's second law for rotations and the definition of torque. When you're calculating torques, right, you say, it's R times F times sine of beta, where beta is the angle between R and F. That's how you calculate a given torque. Maybe torque from torque of gravity, okay, force of gravity, this is the radial arm for gravity from the pivot point. Newton's second law for rotations is what? It's torque equals I times alpha. This thing is like Newton's second law for linear case, right? This is not how you calculate torques. You might use it to find torque, but this thing is how you relate torque to acceleration, to angular acceleration. Think about this the same way you think about Newton's second law. You use this to calculate each of the components adding up to the net torque. This is net torque right here. So keep that straight. I'm just going to check one more thing to make sure I'm telling you guys the last bit. Two-sided cheat sheet, I told you that. Tau right. Right. I think that's going to do it for now. And next week we're going to keep moving with new material. On Thursday, though, is Q&A. You guys can come ask me questions about the exam. And we'll see you soon.